previously we defined ring homomorphism, and in this video we want to look at some important properties and examples of ring homomorphisms. So let's just recall. So let's say R and S are rings, and we're not putting any other restrictions on them. They don't need to have identity, they don't need to be commutative, and so on and so forth. So this function phi from R to S is called a ring homomorphism if you can split the addition up this way. So phi of A plus B is phi of A plus phi of B. Phi of A times B is phi of A times phi of B. And then an important object is the kernel of phi, and that's going to be all elements from the domain that get mapped to 0. So notice it's all R and R such that phi of R equals 0. So now the first thing that I want to do is prove this important proposition that says that the kernel of phi inside of R is an ideal. Okay, great. So let's see how this proof goes. So the first thing that we need to prove is that it's a subring. And for that, we'll use something called the subring test. It says that A is a subring of R if and only if for all A and B in A minus B is in A, and A times B is in A. So that's what it takes to be a subring. Okay, great. And obviously that's the subring test. The definition of a subring is a little bit different than that. You know, it is a subset which is a ring itself, but it follows from that over there. Okay, so let's go ahead and prove that the kernel is a subring first using the subring test. So let's suppose that A and B are in the kernel of phi, and let's notice two things. Let's notice that if we do phi of A minus B, that's going to be the same thing as phi of A minus phi of B, using the fact that phi is a ring homomorphism, and then that's going to be equal to 0 minus 0, which equals 0. But that tells us that A minus B is inside the kernel of phi. Now let's also notice that phi of A times B is the same thing as phi of A times phi of B, which is 0 times 0, which is 0. But what that tells us is that A times B is in the kernel of phi. So we have this closure under subtraction and we have this closure under multiplication, which tells us that the kernel is a subring. Okay, great. Now the next thing we need to do is show that the kernel is an ideal. In other words, it has this absorption property. So let's do that here. So let's suppose that A is an element from the kernel of phi and R is an arbitrary element from the ring. So we need to show like left absorption and right absorption because we don't know anything about commutativity here. And then, so we'll do that in the following way. So let's notice if we do phi of A times R, that's going to be phi of A times phi of R, but phi of A is 0, so that's 0 times phi of R, but we know that that is equal to 0 because anything multiplied by the additive identity is 0. That's a nice exercise to do. So notice that's our right absorption property. We're absorbing this R multiplied on the right into the ideal. So now let's look on the other side. So that tells us phi of RA. So it's going to be essentially the same thing. This is going to be phi of R times phi of A, but that's going to be equal to phi of R times 0, but that's going to be equal to 0. So what that tells us is that AR and RA are in the kernel of phi, but that's exactly what we need in order to show that the kernel is an ideal. So it's a subring that has this absorption property, so in other words, it's an ideal. Okay, I'll clean up the board and then we'll do some more of these important little results and some examples. The next result we want to prove is actually a generalization of what we just did. So let's go ahead and suppose that J is an ideal of the ring S, which is the codomain of this homomorphism. Then phi inverse of J, in other words, the inverse image of J is an ideal from R. So let's just recall that the inverse image is all elements from R that get mapped into J. Okay, so we are going to need to prove that this is a subring first, and we'll use the subring test just like we did on the last board. So for a subring, so let's suppose that A and B are in phi inverse of J, and let's recall that the entry phi to be inside of phi inverse of J means that phi of A is inside of J and phi of B is inside of J. Okay, so now let's go ahead and notice that here we can say phi of A minus B is the same thing as phi of A minus phi of B, but that's going to be inside of J, and that's because J is a subring. And subrings are closed under subtraction. Now the multiplication is going to go exactly the same way. So here we can go phi of A B is going to be equal to phi of A times phi of B. Notice we've got an element from J, an element from J. That's going to land back in J again because J is a subring. Now we need to prove the absorption property for the ideal. So let's go ahead and do that this way. So let's suppose that A is in phi inverse of J. Recall that that means that phi of A is inside of J, and little r is an arbitrary element from R. Now we need to check from both sides because we don't know if this is a commutative ring or not. So let's go ahead and do phi of AR. Notice that's going to be phi of A times phi of R. Okay, but this is an element from S. This is an element from J, but we know that J is an ideal, so that makes this whole thing an element from J, given the fact that J is an ideal. So again, this is an element from J, this is an element from S, so when you take their product, you have to land inside of J by the absorption property inside of the codomain. Okay, good. And then similarly, we can do phi of RA. That's going to be phi of R, phi of A, but that's going to be inside of J for the same reason. We have a multiple of, we have an element from S times an element from J. That's going to be absorbed into J. Okay, so all of this tells us that phi inverse of J is an ideal. Because notice what we have here is that A minus B is inside of phi inverse of J by this line. A times B is inside of phi inverse of J by this line. And then A times R is in phi inverse of J by this line, and then so on and so forth over there. So let's go ahead and add these down here. So notice this implies that A times R is inside of phi inverse of J. This tells us that R times A is inside of phi inverse of J by the definition of the inverse image. Okay, now why is this a generalization of the very first thing that we did? Well, notice if we take J to be the zero ideal, then the inverse image of the zero ideal is the kernel, which we proved that was an ideal on its own, but it will follow from this result. Okay, I'm going to clean up the board, then we're going to look at a couple of examples. Okay, the first example we want to look at is this. So 2z is isomorphic to 3z at the level of groups, but not at the level of rings. So let's go ahead and show that this is true as groups, and this is actually super simple. We can just take the map phi from z to nz, where phi of m is equal to m times n. And again, it's easy to show that this is a homomorphism, that the kernel is equal to 0 and that it's onto. But that makes it an isomorphism. Okay, so I won't check all of those details, but that's easy to show. But what this tells us is that NZ is isomorphic to Z, and that's true for all n. So that means 2Z is isomorphic to Z and 3Z is isomorphic to Z. But what that does is that makes 2Z isomorphic to 3Z by the transitive property of isomorphisms. So now let's show as rings. Let's go ahead and suppose that I've already used phi, so let's use psi from 2Z to 3Z is a ring homomorphism. And now let's go ahead and see that this implies that psi of 2 is inside of 3Z. In other words, psi of 2 is equal to 3 times n for some integer n. Okay, now we're going to do two things. We're going to use the fact that 2 times 2 is the same thing as 2 plus 2. So let's notice that psi of 2 plus 2 is going to be equal to psi of 2 plus psi of 2. But that's going to be equal to 3n plus 3n, which equals 6n. But 2 plus 2 is obviously equal to 4, and that's the same thing as psi of 2 times 2. But then since this is a ring homomorphism, that's the same thing as psi of 2 times psi of 2, which is going to be 3n times 3n, which is equal to 9n squared. But that's going to tell us that 9n squared is equal to 6n. Now the important thing here is that we know for a fact that n is not equal to 0 because 2 is not equal to 0, and since this is 1 to 1, it has to map to a non-zero element over there in the range, which means we can divide by n. So I'm going to divide both sides by n and by 3, and that's going to give me 3n equals 2. In other words, n equals 2 over 3. But notice that tells me that 2 over 3 is an element from the integers, which is a contradiction. So in fact, what we've shown is something stronger. Not only are these guys not isomorphic as rings, but there's in fact no ring homomorphism from 2Z to 3Z. Okay, great. I'm going to clean up the board, and then we're going to do another example like this. We've got another similar example to look at. So Q adjoined root 2 is isomorphic to Q adjoined root 3 as groups, and I should say as additive groups here, but not as fields. So I'll let you guys check that they're isomorphic as groups. One thing I will say is that the isomorphism that you'll use for groups is that A plus B root 3 is going to be sent to A plus B root 3. Sorry, I should have said A plus B root 2 is going to be sent to A plus B root 3. So that's going to be your isomorphism as groups. Now let's go ahead and show that they cannot be isomorphic as. So we'll do this using pretty much the same strategy that we did for our last example. So let's suppose that phi from Q root 2 into Q root 3 is a field isomorphism. Okay. And what that tells us is that phi of root 2 needs to be mapped to something in Q adjoin root 3. Well, we know everything in Q adjoin root 3 has the form A plus B times root 3 for some A and B, which are elements from Q. And I should say that these are not both 0. And we know that because if they were both 0, then this element on the right-hand side would be equal to 0, but then we would have phi of root 2 equals 0, but then also phi of 0 is equal to 0, which means it would not be 1-to-1, which means it would not be a field isomorphism. So we have all sorts of trouble then. Great. And now we're going to use the fact that root 2 times root 2 is equal to 2. So let's go ahead and see that. So phi of 2 is going to be phi of root 2 times root 2, which is equal to phi of root 2 times phi of root 2. Okay? But notice that's going to be the same thing as a plus b root 3 quantity squared, which we can simplify by foiling this thing out. So notice that's going to be a squared plus 3b squared. So that's what we get from the two ending terms. And then plus 2ab root 3. Okay, so that's what we get for that guy over here. And now we want to do some simplification over on this side as well. So notice this is going to be equal to phi of 1, this is going to be equal to phi of 1 plus 1. So 2 is obviously equal to 1 plus 1. But now that's going to be the same thing as phi of 1 plus phi of 1. And then another thing that's easy to check is that if you have two rings with a multiplicative identity, then the multiplicative identity in the domain has to be sent to the multiplicative identity in the codomain. So I won't check that, but that's easy to check. So notice that 1 is the multiplicative identity in the domain, and 1 is also the multiplicative identity in the codomain. So this thing is actually just 1 plus 1, which is equal to 2. Okay, now we're good to go. So notice that we have our extreme left-hand side and our extreme right-hand side. We have 2 is equal to a squared plus 3b squared plus 2ab times root 3. But notice that I'm going to erase this 2 over here and rewrite it as 2 plus 0 times root 3. And then by the fact that this is really like a vector space over Q, or there are a bunch of ways to think about it, we know that the coefficients of just the rational numbers on either side need to be equal, and the coefficients of root 3 on either side need to be equal. So that tells us that 2 needs to be equal to a squared plus 3b squared. And furthermore, 0 needs to be equal to 2ab. In other words, a equals 0 or b equals 0. Now, I'm actually going to erase the board, bring that to the top, and then we'll continue on. So we've worked this down to the following point. So if we assume that phi of root 2 was equal to a plus b root 3, then we ended up with a squared plus 3b squared equals 2. And either a is 0 or b is 0. So let's go ahead and see why none of these work. So let's suppose that a equals 0, so that'll be like case number 1. But that tells us that 3b squared equals 2, which tells us that b squared equals 2 over 3. But then that tells us that root 2 over 3 is a rational number, which that's a contradiction. So I won't prove that, but you can prove that via simple methods, maybe like a proof by contradiction or something. So the next way is going to go very, very similar. So let's go ahead and suppose that b is equal to 0, which is the other case. And that's going to give us a squared equals 2, but that tells us that root 2 is a rational number. But again, that's another contradiction because we know that the square root of 2 is not a rational number. So notice both of the possible cases led to a contradiction, which tells us that there's actually no type of field isomorphism between these two fields. Okay, good. So I'm going to erase the board, then we're going to look at one more example like this. For our last example, we want to examine all ring homomorphisms from Z cross Z to Z. So here we have the product of two rings, and so all of the operations happen component-wise. So it's component-wise addition and component-wise multiplication. Okay, so maybe the first thing to notice is that Z cross Z has two generators, and it's generated by 1, 0 and 0, 1. So in fact, if we can get a feel for what happens to 1, 0 and 0, 1, then we're good to go. So let's go ahead and suppose that phi takes 1, 0 to m and it takes 0, 1 to n. So notice that tells us that phi of 0, 0 equals phi of 1, 0 times 0, 1. So that's like maybe easy to see because the multiplication happens component-wise, and 0 times 1 is equal to 0. But that's going to be equal to m times n. So notice that also that phi of 0, 0 has to be equal to 0 given the fact that this is a ring homomorphism. The additive identity in the domain has to go to the additive identity in the codomain. So that tells us that m times n equals 0, which implies that m equals 0 or n equals 0. Okay, we determined that if we've got a ring homomorphism from Z cross Z to Z that sends 1, 0 to m and 0, 1 to n, that either m is 0 or n is 0. So now let's also notice this. Notice if we have phi of AB, that's going to be the same thing as phi of 1, 0 added to itself A times plus 0, 1 added to itself B times. But now using the fact that this is a ring homomorphism, we can split all of those up. So that's going to be phi of 1, 0 added to itself A times plus phi of 0, 1 added to itself B times. But it's easy to see that that's going to be A times m plus B times n, assuming that m is equal to phi of 1, 0 and n is equal to phi of 0, 1. So this is the general property of what's going on with this ring homomorphism. But now we know that one of these is equal to 0. So we can say case number 1, which would be m equals 0. So that means that phi of AB equals B times n, which tells us that the kernel of phi is going to be equal to this entire first component, so Z cross the 0 element from this second component, so we can write that as a set like this, and then the image of phi is going to be all multiples of n. And that's kind of easy to see. And then case number 2 is going to be very similar, and that is if n is equal to 0. So that tells us that phi of AB equals m times a, because we know that n was equal to 0, but that tells us that the kernel of phi is equal to the 0 element in the first component cross the entire second component, and then the image of phi is equal to mz. So what we have here is that if we have a homomorphism from Z cross Z to Z, we in fact have to collapse one of the components from the domain in order to get this to work out any way that we can. And that is seen by the fact that one of the components is always entirely in the kernel. All right, so this is a good place to stop.